like which primitive works are values.
Well, we need to determine why it's correct. Is it this can be that somebody put in, or this can be considered and we want to go before you see the most obvious they have. Hey, Cameron.
Great. So let's get started, everyone. So today we're going to have a shorter lecture. I'll plan to finish around 2, and if I keep going by 2:15, so I definitely have to stop, and then there'll be chance for peer feedback on your project so far. So I hope you've all been making some pretty nice progress on your projects. So they don't have to be complete at this point, but enough to get feedback. And so we'll leave some time for that in the schedule. Just to review, we're in the dimensionality reduction part. We've kind of covered the basics with the singular value composition and PCA. We talked about scaling this up to fairly recent changes in how people approach very large scale on the last 10 years that changed stuff that had been fixed for like 50 years. And then we talk about modeling and caring more about the choice of the distance. We'll kind of do something in between now, talking about a different fundamentally kind of, I think the obvious modeling goal you would like to have, and then we'll talk about the properties about it. And this will work in very high dimensions. And this kind of, the history of this is this work kind of kicked off this very large scale kind of, the idea we'll talk about was actually historically before all the stuff on the sketching, and it kind of led into that, although it's not as useful as those approaches. So it'll be a little bit different modeling, and I'll be talking about very, very, very high dimensions and what to do in those cases. And then we'll get a bit back to the modeling in the lecture on Monday. Someone pointed out that the dimensionality reduction homework on Canvas, it says it's due next Wednesday. I will correct that after class. Will be due in 2 Wednesday, so in 2 weeks. This assignment is almost ready. The TA is kind of just reviewing it, and then I'll post it in the next day or so, hopefully. Great. Yeah, questions?
And this says due November 5th. It is due November 12th.
Yeah, it'll be due on the 12th. Yeah. So yeah. So I just learned about that a few minutes ago. I'll correct it after class. After all my meetings with all of you after class. Yes. Okay, so let's talk about this random projection approach. And so what we have here as the input data, x1, x2 up to xn, and these we'll think of them as a subset of our D. And so we're going to think now that D is extremely large. Okay, and today we'll be talking about the paradigm where this is maybe 100 million. When I was in grad school 15, 20 years ago, these large companies on the internet, like ones that are no longer in business, like Yahoo and stuff, but also Google at the time, they were collecting data sets that had this large of dimensionality, keeping track of very large things like the stuff representing the entire web. And they wanted to reduce the dimensionality of these things. And so this was kind of very relevant at the time. And so we still have data sets this large. And the goal now is to map this to a goal is a data set Q1, Q2 up to Qn, which is going to be in RK, where K is going to be much less than D. And we're going to think of K as about 500. Okay, it could be larger than 500, but it could be like a few thousand would probably be fine. This is like the dimensionality of these kind of these layers of these large language models, right? This is a scale that you can work with without being painful just to read one of the data points, okay? And so we'd like this. And so we talked about a number of approaches that kind of, I didn't really write down what it was, what the guarantees were. We could write this down with singular validity composition and PCA, and that it was minimizing the sum of all the projections. But what did that actually mean and what it's preserving here? Okay, and so now the goal is so that for all pair xi, xj in X, okay, I want this to hold for all pairs. I want to have the property that if I look at the distance between qi minus qj, and we're working in the Euclidean distance, then this is going to almost match the distance in the high dimensional space. Okay, so if I look at the Euclidean distance in the high dimensional space and I shrink it by a small amount, we can think of there's some error parameter, error tolerance, epsilon, and we can think of this should be in 0, 1, but you could think of epsilon maybe equals to 0.1 or 0.001. So either within 10% or maybe within 1% of the distances. Okay, so if distance is really small, I want them to still be small. Distances that are large, I can change in their absolute distance, so some amount, but the relative scale should be about the same. So large distances stay large and small distances stay small. This, and so I don't care about the scale. If I took all the values and I multiplied them by 100, I changed the units, this property will still hold, right? So it's invariant to what the scale is. It's a relative error here. And this is kind of a very strong and kind of nice guarantee that would be nice to have, right? So if I care about, right, so if I want this guarantee, this is kind of the holy grail of dimensionality reduction. And it's because if I ran something like a nearest neighbor search algorithm or a clustering algorithm after I did this form of dimensionality reduction, well, it would still, the cost function would still hold within this kind of this error tolerance epsilon, within 10% or within 1% of what I was actually doing before. But now I've reduced the dimensionality a lot, right? So I can pass guarantees directly to all the sorts of things I want to do. This is not necessarily true about all the stuff we talked about the previous few lectures with things based on PCA. Depends on what is the tail of the distribution. I'm kind of chopping off the tail, the dimensions that have too much, have the least information, but if I chop off too much, I might distort kind of a lot of the distances. And this has a guarantee that it's for all pairs, right? So for every distance. The PCA style distances does not have a guarantee for all distances. It could be that most of the distances are guaranteed within 1%, but there are a few distances that are distorted a lot, right? By 50%, or, I've reduced the distance between things a lot. You could think of, there's a subspace, most of the data lies here, but there's one or two kind of outlier points that I have to project down onto this. Now, if I do a nearest neighbor query, I might choose those as the nearest neighbor, even though they're actually very far away. Okay, this guarantees everything is approximately the right distance here. So it's a very kind of strong guarantee. This is what I'd really like to have. Okay, so this has been studied a lot. It's very nice. If I want to work with super high dimensional data for a bunch of problems, you often want to do this first to reduce the dependence on the dimension. Okay, so I'm going to have some good news and some bad news about this. The good news is we kind of completely understand this problem at this point, and we kind of exactly know how well we can do. But the bad news is it basically will only work in this sort of paradigm where D is extremely large and K, I can get down to about 500 or so, right? Maybe 200 if I'm lucky, but it might need to be 1,000 or 2,000, okay, for this to actually to get something like this. And it'll depend on epsilon. The smaller I make epsilon, the less error tolerance I have, the more dimensions I will need. Okay, so we basically completely understand this trade-off here. Okay, and the algorithms for it for doing this is actually very simple. Okay, so that's the good news, but the bad news is that it only works for really, really high dimensions, and I'm not going to be able to get down to a much smaller dimension, at least in all cases. In some cases, if the data is low rank, then I can get down to very low dimensions without incurring a lot of error, but I don't necessarily know that ahead of time. If I knew that ahead of time, then maybe I don't have to do this. I can do something else that's that's clever instead. All right. So we're going to solve this with what's called the Johnson Lindenstrauss, and I'll call them random projections. You can say something without randomness, but basically everyone uses the random version. Okay. And so this was kind of a lemma in a long paper that turned out to be kind of the most important consequence of some work from like in the 1980s. All right. So what we'd like to do is to determine a mapping mu from RD to RK. And so I want to distort the distances with distortion one plus or minus epsilon on so all these distances. And so what we're going to do is we're going to define a set U1, U2, UK of these vectors. Uj is going to be in RD, and Uj, the norm of this is going to be 1. Okay, but actually I don't want this to be 1. I'm going to want it to be the norm, the square root of D over the square root of K. Okay, and I'll explain why that is. So I can find these vectors, I can normalize them so their length is 1, and then I scale them up by the square root D over square root K. Okay, so I'm going to have this, and then I'm going to define this mapping. Mu of X is going to be this pi of U1 UK projection of X onto this sort of subspace. So for this is going to give me a value Q, and it's going to work as follow that QJ. So this will be the jth coordinate of Q is going to be defined as just my input X dotted with Uj. Okay, so this will be the jth coordinate of this vector Q, and I'm going to have K of these vectors, U1 through UK, and each dot product is going to give me one of the coordinates. Okay, all Okay, I'm not enforcing that the U1 through UK are going to be orthogonal to each other. Okay, I'm going to choose them so they're approximately orthogonal, but I actually don't need to enforce that they're orthogonal. I could, and actually the first proof by Johnson Lindenstrauss actually found them and then orthogonalized them and then did this, but it turns out you don't need to do that. Things work basically just as well. And I will, okay. So this is the construction. I need to define the set U1 through UK, and then this defines my mapping down to low dimensional space, right? So this should look like what I did with PCA, where I took X and I did the singular value decomposition after I did a centering of X, and then I took the right singular vectors and I'm projecting onto here. So it's the same operation, but I need to pick these so that it preserves all the distances instead of just one of just the top K that has the most variation in the data. Okay, so how do we choose U? How do we choose UJ, right? So how do I choose one of these vectors? I'll give you a hint, it's going to be random somehow. Okay, good. So what does it mean to choose that at random? Good, so I'm going to choose this at random. It's a random projection. Uniformly, what does uniformly mean? Every what? Okay, but I have to be, so it's a d-dimensional vector, and let's say its norm is 1 about. How do I do this? How do I get it so it has the right? So yeah, so I need to generate a high dimensional vector so that it could be any high dimensional vector roughly with its norm 1. How do I do that? Did we talk about this earlier in the semester? Maybe in the LSH section? No? Okay. I can do what? Yeah, well, so I can use a Gaussian random variable, not a Gaussian mixture. A mixture means it's a bunch of Gaussians that are kind of like a clustering. That's defining distribution, but just I want to use a Gaussian random variable. So how do I do this? I'm going to generate a vector G. I'll call this G in RD. So each coordinate GJ is going to be from a normal distribution. Okay. And so then G in total, which is a d-dimensional vector, will be from a d-dimensional normal distribution. Okay, a normal distribution is something we know how to sample from. In fact, there's something called a Box-Mueller transform from a uniform distribution convert to a normal distribution. And the normal distribution has the nice property that is completely symmetric in every direction. So if I sample from normal distribution, then I take it and I then do this sort of normalization. It lies on the hypersphere, and it's independent of which direction. So it's a random direction in the space. Okay, so then I'm going to say U is going to be G divided by the norm of G times square root D over square root K. Yeah, so this makes it so it's a unit vector, and then I told you I needed the scale, right? Which I'll explain a bit. So this is how I generate each of these vectors U, right? This is one vector UJ, and I'm going to do K of these vectors. Okay, K vectors at random. I'm just going to project onto these random vectors. Okay, so it seems like, why would this work for reducing the dimension? PCA was very structured. It looked at the data. It did this kind of magical kind of eigen decomposition, SVD decomposition, and found the most informative directions. I'm not doing this here. I'm just picking ones at random. Why should this work? Okay. So I mean, I've basically explained this is the whole algorithm here. Okay. Hopefully it's very simple. Again, I pick these, I fill up these k vectors that are d-dimensional Gaussian vectors. Each coordinate is a normal. And then I normalize them, scale them by square root d over k. And then I do this projection to get each coordinate of a point Q as a dot product with one of these. Okay, so this is the whole algorithm. So why is this useful? Let's look at, so why does random projection work? Okay, so let's look at U, which is going to be ND01, right? Divided by I'll say, and then U bar is U divided by the norm of U, right? So I have one random unit vector. And now I want to look at some pair of distances, xi minus xj, right? In fact, I'm going to write this as a single vector z. Okay, so if I look at the difference between them, between two vectors I care about, the difference between two vectors is a vector. This is a vector z. And basically, I want the property that the expected value of the dot product of z times u, dot product with u, right, where the expectation is over the choice of u here. I want this to be exactly 1 over d times the norm of z, the norm squared of z. It's the square of this dot product. Okay. Okay, so the square of this dot product, I want it to be exactly this, the 1 over d times the squared norm of z. So if I took my original vector z and I wanted to preserve its length, and I wanted to say, what if I took a dot product with u, I square it, look, what's the expected value of that? I want it to be exactly 1 over d here. So let me kind of explain why this statement is true. Okay, let me kind of explain roughly why this is true. And that I can say that the norm of z, the squared norm, remember this is going to be j equals 1 up to d of zj squared, right? So the squared norm, I'm just taking all the coordinates of it and I'm squaring them and I add them up. That's the definition of the squared of the two norm here. If I took the square root of this is the Euclidean length of it from 0. Okay, and this is with using the coordinate basis, right? So this is I can write z, right? If this is z, I can look at this is z1, this is z2, this is z3, z1, z2, z3, right? And I can write it in this coordinate system, and I square each of the terms in the coordinate system, right? This was a choice of the coordinate system. But what if instead I took a different coordinate system, right? So this is v1, v2, and v3, where v1, the norm of each of these is 1, and v1 and v2, everything is orthogonal to each other. A different coordinate system here instead, right? If I took a different coordinate system, well, then I can also write the norm of z here. This can also be equals to j equals 1 to d of vj z squared. So I can also look at the norm of it, the length of the vector z, by projecting it onto the blue coordinate system instead. As long as these are orthogonal vectors, I can write the norm in this way. I just change the coordinate system. This is kind of a rotation of the space. This is what, like, the right singular vectors were an example of this. Okay? So now what if I picked a coordinate system at random, okay? And then I picked one of the d vectors at random. Okay. I know that the norm of z squared is exactly this, but I picked one of these d terms at random, right, in this coordinate system. So this vj is, if I pick one vj equals u at random, well, I know the total norm is this, and so the 1 over 1 out of d of these things is exactly this term. Right, so that gets me exactly this, 1 out of d times the squared norm of this. So if I pick one direction at random and I project onto it, I get an expectation 1 over d of the squared norm. Okay, so it's an and if I multiply this by d, I get an unbiased estimate. All right, so that means that d times z u squared, the expected value of this, is equal to z squared. It's an unbiased estimate of the squared norm here. Yeah.
Isn't it supposed to be orthogonal?
Is
Like the basic of the unit vector? And
if u is a unit vector?
I mean, u is like the in the right angle. So b should be in the right angle and expect.
Yeah, but I picked a set of d of them that are all right angles to each other. And then I picked one of them.
Yeah, all need to be.
Well, if I just pick one, it's an unbiased estimator. Yeah, there are d minus 1 other ones that are right angles to it, but I'm going to ignore those. Right? The original proof kind of picked a subset of k of them, which are all right angles to each other, but you don't have to worry about that. If I just pick one of them, it's an unbiased estimate. If I scale it by d, right, the squared norm, I get an unbiased estimate here. Right? So if I pick one random direction, I project onto it, I multiply it by d, I get unbiased estimate of the square of it. And I want to kind of approximate the distance, so I divide by square root d of my estimate to get approximate the distance. Okay. 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 So now I want to take the average. So I want to say that now, let me take this. So the point here being that this is unbiased. And also, so now if I say the expected value of d of, let's say, 1 over k, j equals 1 up to k of d times z uj, right? So if I look at this now, I take the average over k of these, right, of this term, it will also be an unbiased estimate of this distance. Okay, so if I do an average over k of them, it's also an unbiased estimate. And in fact, I can I can do a little bit of algebra here, and I can say, well, this is d over k, and I can push all of these terms inside of here, and this is z yeah, it's the norm of z times a u vector squared, where this u is now a matrix that encodes U1, U2 up to UK. So if I concatenated these together, I can write it in this way. Okay, and if I wanted to push this inside of here, it should goes through the square, so it becomes the square root of d over k. Okay, so this is roughly how the algebra works. Okay. Okay, so this kind of gives an unbiased estimate. It doesn't tell me how many I need. So let me just briefly tell you how you get that. I won't go into all the details. I just want to give you the intuition. So I can say that if I choose, so let's see, if you apply a Chernoff-Hofting bound on k random variables xi, where I have something which is 1 over k xi, then I can say something like the expected value of m, or no, I can say that the expected value of, or the probability that the difference between m minus the expected value of m is greater than epsilon is something like is less than delta if k equals roughly 1 over epsilon squared times log 1 over delta. I'm going to get a bound that looks something like this. Okay, remember from Chernoff-Hofting bound, if you've seen this before, it's kind of a tail bound. I get a bound that looks kind of like this, and I'm not going to go through the details. In fact, you cannot apply the vanilla Chernoff-Hofting bound. You need something that has these sub-Gaussian random variables. You need to say something about this. So these need to be kind of Gaussian. There's a special form you can get, but I need something like this number of things to get epsilon error here. Okay, and it turns out this is roughly the right intuition, and this turns out to be part of the bound. This will work for any one question I ask. I'm looking at one quantity and the difference here. So this works. This approximately holds for any one kind of z equals xi minus xj, right? So this is a pair. Okay, so if a pair of points I want to preserve the distance, I can look at this analysis, say I projected onto this many different kind of subspaces, this many subspaces, and for any one pair, I will get 1 plus epsilon approximation of the error. Okay, now I need to, but I want this to hold for all the distances at once. Okay, to hold for all distances, for all distances, I'm going to make this delta prime. I'm going to set delta prime equals to delta divided by n squared, because n squared is approximately the number of pairs. Okay, it's n choose 2, but approximately n squared. Okay, so I'm going to instead say I want this hold for all distances, so I'm going to make this delta prime, the probability of failure that something goes wrong, much smaller by a factor of n squared. Okay, but this is inside of a log term here. So this allows me to say, well, this is now k for all distances is 1 over epsilon squared log of n squared over delta here. And this is, can I simplify this big O expression? So I'm going to see where I can simplify what's inside the big O. There's one thing I can remove. which two? The n squared. Yeah, I can write this as 1 over epsilon squared log of n over delta, because if I have a power inside of a log, the 2 comes out in front, and now 2 is a constant. It goes into the big O. Okay, so this is the bound. This is the bound that is stated for the number of dimensions you need to get a Johnson-Lindenstrauss random projection type bound. Notably, it scales with 1 over epsilon squared. So if I want 10% error, I need like a factor of 100 here. And 1% error, I need a factor of like 10,000. Okay? What people usually pay attention to is the log n. I need number of dimensions I need grows logarithmically with the number of points. Okay, so if my number of points grows, the number of dimensions grows much, much smaller than I need to approximately preserve all the distances. When n gets really, really big, the 1 over epsilon, let's say 10% error, that's a factor of 100, not a big deal. What's interesting is with the number of data points, it grows very slowly. Okay, and so from a theoretical point of view, this is kind of very interesting. So instead of needing 1 point for every dimension to make sure I capture everything as full rank, I only need roughly logarithmic in the number of dimensions. Seems a lot smaller, but in practice, this number is like 500 or 1,000. Okay, so from a theoretical point of view, this got so much attention, people got so interested in it, and it kind of jump-started a bunch of the sketching stuff. They're like, oh, we can reduce the dimension to not be linear in the number of points, but to be logarithmic, and this is a big deal. But kind of only gets you down to like a few hundred dimensions at the least, and probably around 1,000. Okay, this is also why you see large language models. They're operating in often the dimension of the subspaces they work in was it on average like 1 or 2,000? Where's well, maybe Oliver knows, so 4,000, okay, yeah, so they're embedding, maybe it's going to keep growing, but my guess is around 1 to 4,000 is roughly where the sweet spot's going to be. After you encode it that much bigger, my guess is maybe they don't need 4,000 even, that you can capture so much information in like a few thousand dimensions. There's not going to be much need to go above that, because the amount of information you need, the number of points of information you need to capture in there roughly scales with log n with some factor in front. And I think we've kind of saturated this first factor, and the log n is now going to grow very slowly. Okay. Okay, so this was this is basically all I wanted to say about this topic. You need to have this sort of guarantees to do things like approximate nearest neighbor search, approximate clustering, and approximate regression with guarantees, okay? But it's kind of bothersomely large to deal with sort of data sets we would work inside a class usually. So it's hard to really see the results on moderate-sized data sets. You really need to get really big before this starts start to kick in. So the PCA stuff should be, PCA eigendecomposition should be your first thing to try. And if it's too slow there, you can speed, talked about last week about maybe how you can speed this up with some sketching ideas, but these won't get you as low of a dimension. And you basically cannot beat this bound. There's lower bounds, even for deterministic algorithms that look at data that basically need roughly this many dimensions. So you basically cannot beat this randomized algorithm. The convergence is quite good. It's in the log term, and so if this is basically what the right answer is needed to get this very strong sort of guarantee where you approximate all the distances and you guarantee to do that. The one other advantage of this that PCA does not have in all those approaches, to define this function, right? This function, which is projecting down to a lower dimensional space, I did not need to look at the data kind of ahead of time to define the function. It's completely oblivious to the data. Maybe I needed to know how many data points I would ultimately want to kind of ask questions about, because that defined how big K needed to be. But I don't need to know what the structure of the data is. So if I have new data points and not too many of them that come afterwards, I can still have the guarantees even with this projection. Where with PCA, I may not have that. If I add new data points, I may need to change how I define this projection. I can define this once and just stick with it. Great. So okay, so let's any questions on this, and then we'll wrap this up, and then we'll do a bit more modeling on Monday and feature selection and maybe some other types of feature encoding algorithms on some Monday. Okay, great. Let me